Modern machine learning systems operate in environments where dozens, sometimes hundreds, of variables interact simultaneously. To model these environments, a system must track how every variable relates to every other variable, a calculation that requires computing their joint probability distribution. This diagram demonstrates the exact computational cost of that mathematical reality. Specifying a general joint distribution over a set of binary variables requires calculating 2 to the n-1 parameters. A small system of just 2 variables requires 3 parameters, but as we scale n toward 100, the parameter count climbs into the nonillions. At 100 variables, the parameter count exceeds the physical memory limits of any computing hardware on Earth. The system hits an absolute mathematical wall. Yet everyday diagnostic AIs, sequence models, and spam filters routinely process inputs with thousands of features. We have to ask how they calculate exact probabilities across these massive networks without triggering this combinatorial explosion. The answer lies in discarding a flawed assumption. Treating all variables in a high-dimensional space as mutually dependent is mathematically intractable. Forcing a system to compute every possible interaction guarantees it lacks the resources to compute anything at all. We bypass this limit by exploiting structural sparsity. In any physical or logical system, most variables do not directly influence every other variable. The causal connections are sparse. We define this isolation through conditional independence. If 2 variables only interact through an intermediate event, they become mathematically independent once that specific third variable is known or observed. Probabilistic graphical models, or PGMs, provide a formal visual language for mapping these exact independencies. Here, the intractable matrix collapses into a directed graph. The lines or edges encode exactly which variables directly influence which others, and more importantly, which ones do not. By isolating variables that have no direct statistical relationship, the graph topology fragments the massive joint distribution into a product of manageable local clusters. In high-dimensional probability, drawing the graph is not a visualization exercise. The topology is the exact algebraic blueprint required to factor the distribution. When variables exhibit a generative or causal structure, we map them using directed graphical models, commonly known as Bayesian networks. In these networks, the edges are drawn with arrows to indicate the direction of influence. This diagram defines the exact factorization rule for a Bayesian network. The total joint distribution factors into a product of local conditional distributions. Each node's probability relies strictly on its direct parents, the nodes with arrows pointing directly into it. Nodes situated at the top of the hierarchy has no parents. Their probabilities are given entirely by their marginal, prior distributions. We see the extreme efficiency of this rule in a naive Bayes classifier. This algorithm assumes that a wide array of observed features are all conditionally independent from one another, given a single known class label. We graph this as a star structure. Because the central class node dictates the state of the surrounding features, those features do not require edges between themselves. This strips out millions of unnecessary calculations. By strictly mapping causal directionality, Bayesian networks fracture a dense, unreadable web of data into highly isolated, highly computable parent-child relationships. To verify if these models are actually saving computational power, we need a way to read conditional independence directly from the arrows. We do this using a set of graphical rules called D-separation. This visual shows a simple linear chain, passing from node A through node B to node C. If node B is unknown, information flows freely through it, meaning A and C are dependent. However, conditioning on the middle node, meaning we observe its actual value, blocks the path. Learning the state of B isolates C from A, rendering the outer nodes conditionally independent. A fork structure represents a different dynamic, a single common cause, node B, generating 2 distinct effects, nodes A and C. The same separation rule applies. Once we condition on the common cause, the path between its effects is blocked. A and C become independent. In both chains and forks, observing intermediate data acts as a blockade. The act of gathering information simplifies the network by severing statistical ties. But treating observation as a universal simplification mechanism leads to a severe reasoning error. Conditioning does not always isolate variables. Sometimes it entangles them. This graph illustrates a collider. Here, two distinct causes, rain and a sprinkler, both point into a single common effect, wet grass. In their natural state, rain and the sprinkler are marginally independent. The weather does not control the sprinkler timer, and the sprinkler timer does not control the weather. The paradox occurs when we observe the common effect. If we step outside and see that the grass is wet, the path between the causes abruptly opens. This forces a phenomenon known as explaining away. If the grass is wet and we check the weather report and learn it did not rain, the likelihood that the sprinkler was running immediately spikes to near certainty. Confirming the state of one cause dictates the probability of the other. The act of observing the wet grass transformed two entirely independent systems into strictly dependent variables. Misunderstanding colliders leads to flawed AI reasoning, as observing new data can inadvertently entangle previously isolated systems. Bayesian networks rely on clear causal chains, but many systems possess no generative direction. A classic example is analyzing pixel arrangements in image processing. One pixel doesn't strictly cause the color of the pixel next to it. They simply exist in a symmetric physical relationship. To map symmetric associations, we use an undirected graphical model, or Markov random field. Stripping the arrows from edges removes the presumption of causality. Reading independence here requires simple graph separation. A node's Markov blanket is strictly its direct physical neighbors. If those immediate neighbors are known, the central node is completely conditionally independent from every other node in the entire image. Predicting its state requires zero information from outside its localized blanket. But removing causal direction changes the underlying math. Without parent-child probabilities naturally capping at 100%, undirected models calculate association using clique potential functions. These potentials are unbounded, meaning the system requires a global normalizing constant, called a partition function, to force the final probabilities to sum to 1. Markov random fields perfectly map spatial proximity. The trade-off is the computational friction of solving that global partition constant across the entire grid. This comparison illustrates the trade-offs. Directed models map sequences, while undirected models map symmetric fields. If we structure a directed network as a linear chain, where hidden states generate observed variables, we create a hidden Markov model. Because human speech moves strictly forward in time, one word causing the next, hidden Markov models remain highly effective for speech recognition. Conversely, a computer vision system analyzing an X-ray cannot use a directed sequence. Physical space has no inherent origin point or causal flow, demanding the undirected symmetry of a Markov random field. The physical nature of the data dictates the graph topology. Whether the target is a temporal sequence or a spatial field, the architecture must mirror the environment. We began with a mathematical trap. Attempting brute force probability calculations across hundreds of variables guarantees complete system failure. Sparsity provides the escape route. The rules of D-separation in directed networks and RAF separation in undirected fields give algorithms the mathematical permission they need to ignore massive, irrelevant chunks of a network. Exact inference algorithms, like belief propagation, survive solely by riding the precise, localized pathways defined by these graphs. They update probabilities node by node, blanket by blanket, rather than calculating the entire grid at once. Graphical models serve as the mandatory data structures that transform computational impossibility into actionable machine learning.